we have this problem, oil well problem. An oil well is 1,000 feet deep. An oil well that is 1,000 feet deep is to be extended to a depth of 4,000 feet. So currently the oil well is 1,000 feet deep, and it's going to be extended to a depth of 4,000 feet. So we're going to have to drill 3,000 additional feet. The drilling contractor estimates that the cost in dollars per foot, f of x, for doing the drilling is given by this function, where the output of the function represents the cost in dollars per foot, and the input x of the function represents the depth at which we are drilling. So the deeper we are in the well, the more it will cost to drill an additional foot. So in number 3 it says, estimate the cost of drilling from 1,000 feet to 4,000 feet. What is the cost of drilling an additional 3,000 feet from a depth of 1,000 feet to 4,000 feet? That's what question 3 is asking. Estimate the cost again, but this time estimating the integral using rectangles whose altitudes are measured at the midpoints of each strip, and so on. The sum of the areas of these rectangles is called a Riemann sum R sub 6. Is it close to T sub 6, the trapezoidal sum using 6 trapezoids? So we want to note that the vertical axis for our function will give us the cost of drilling an additional foot at a particular depth, and it's going to be measured in units of dollars per additional foot. And the horizontal axis for our graph tells us the depth of the well measured in feet. So what do we want to know? We want to know how much is it going to cost to drill from 1,000 feet down all the way to 4,000 feet. It's a drilling that's going to cover a depth of 3,000 feet, but depending on how deep you are in the well, the cost of doing the drilling is different. The deeper you are, the more expensive it is. So this function tells you the cost of drilling at a particular depth. And here we have the graph of that function. But if you want to find the cost of drilling the 3,000 additional feet, you have to find the definite integral of the function with respect to x from a depth of 1,000 feet to a depth of 4,000 feet. And the units will be, again, if you look at f of x, it has units of dollars per foot. And if you look at x, it has units of feet. And what you have here is a product. So when you multiply dollars per foot by feet, the definite integral will have units of dollars. And it would give you the cost in dollars for drilling from 1,000 feet deep to 4,000 feet deep. And this problem number 3 is asking you to estimate this cost by finding the area that is under the graph of the function f, above the horizontal axis, between the vertical lines x is equal to 1,000 and x is equal to 4,000. Because this definite integral represents that area, which in the context of the problem would represent the cost of drilling from 1,000 feet deep to 4,000 feet deep, given in dollars. So 3 is asking you to approximate this definite integral, or this area, in a particular way. So let's see how you would do that. Estimate the cost, again, this time estimating the integral by using rectangles whose altitudes are measured at the midpoint of each subinterval. So earlier in the course we learned about partitioning an interval of x values into a number of subintervals. So we have the interval from x is equal to 1,000 to x is equal to 4,000, which has a width of 3,000 feet. And if you divide that into 6 subintervals of equal width, each subinterval will have a width of 500 feet. So these are our subintervals, and I will indicate them with these green vertical line segments. So we have a total of 6 subintervals, and on each subinterval I can draw a rectangle, and I can use the area of each rectangle and add the 6 areas together, and that would give me an approximation for the value of the definite integral. In this particular problem, it says find the area of each rectangle. How? It says this time estimating the integral using rectangles whose altitudes are measured at the midpoint of each subinterval. So what is the midpoint of the first subinterval from 1,000 to 1,500? The midpoint would be at x is equal to 1,250. And the height of the rectangle at that x value would be given by the function evaluated at 1,250, which will give you 26.25. And in the context of the problem, what that means is if you are drilling at a depth of 1,250 feet below the surface, for each additional foot at that depth, it will cost you $26.25. That's what that means. So find the area of this rectangle by using this height of 26.25, and the width would be 500 feet. And it's an approximation. And then find the area of the next rectangle at the depth of 1,750, and the width of the rectangle would be 500 feet. And at the depth of 1,750, it would cost $32.25 to drill an additional foot. So the deeper you are, the more expensive it gets. So for the third rectangle, find the height at the midpoint of the subinterval at 2,250 feet. And at that depth, it would cost $40.25 to drill an additional foot. So you're estimating the area of the region of interest, because obviously it's not exactly the same, but using the midpoints of each subinterval, you're assuming that the cost of drilling would be the same for that 500-foot interval. And of course it isn't. But you make that assumption so that you can just sort of have an estimate for the total cost of drilling an additional 3,000 feet. And that's what you're supposed to do for number 3. Find the area of each rectangle and add them together.